Good morning, everybody. I introduce myself. My name is T. Henson. I am working as assistant professor in the Department of Mathematics, St. Joseph's College of Arts and Science, Cuddalore. So I am going to teach ordinary differential equation for first MSc Mathematics. Unit 3, topic linear equations with variable coefficients. Now we are going to see the following theorem. If pi 1, pi 2, pi 3, pi n are n solutions of L of y equal to 0 on an interval I, then the solutions are linearly independent if and only if the function of x is not equal to 0 for all x in this interval I. Now we are going to see the proof. Suppose if the function of x is not equal to 0 for all x in the interval, if there are constants C1, C2, C3, Cn such that this linear combination is to be satisfied with the following derivatives. So there are equations of 4.1 and 4.2. So these equations are to be satisfied for all x in the interval I. For a fixed value x in I, the above equations are linear homogeneous equations satisfied by C1, C2, C3, Cn. The determinant of the coefficients is just function which is not 0. Hence, there is only one solution to this system, namely C1 equal to C2 equal to C3 equal to Cn equal to 0. Therefore, the functions are linearly independent on the interval I. Suppose pi 1, pi 2, pi 3, pi n are linearly independent on the interval. Suppose there is a point x0 in I such that this function of x0 equal to 0. Then this implies that the system of n linear equations has solutions C1, C2, C3, Cn, where not all the constants C1, C2, Cn are 0. Let C1, C2, C3, Cn be such a solution and consider the function psi equal to C1 into pi 1 plus C2 into pi 2 plus etc. Cn into pi n. Now L of psi equals, and from the above equations we see that psi of x0 equal to 0, psi dash of x0 equal to 0, then psi double dash of x0 equal to 0, then psi n minus 1 dash of x0 equal to 0. So it follows that psi of x equal to 0 for all x in this interval. Thus, this linear combination gives 0 for all x in the interval I. But this is a contradiction to the fact that pi 1, pi 2, pi 3, pi n are linearly independent on the interval I. Thus, the supposition that there was a point x0 in the interval I such that this function of x0 equal to 0 must be false. So we have consequently proved that the function of x is not equal to 0 for all x in this interval I. Next theorem, let a pi 1, pi 2, pi 3, pi n be n linearly independent solutions of L of y equal to 0 on an interval I. If pi is any solution of L of y equal to 0 on the interval, it can be represented in the form pi equal to C1 into pi 1 plus C2 into pi 2 plus etc. Cn into pi n, where C1, C2, C3, Cn are constants. Thus, any set of n linearly independent solutions of L of y equal to 0 on I is a basis for the solution of L of y equal to 0 on this interval. Now we see the proof. Let x0 be a point in the interval I. Suppose pi of x0 equal to alpha 1, pi dash of x0 equal to alpha 2, pi double dash of x0 equal to alpha 3, etc. Pi n minus 1 dash of x0 equal to alpha n. We show that there exist unique constants C1, C2, C3, Cn such that psi equal to C1 into pi 1 plus C2 into pi 2 plus etc. Cn into pi n is a solution of L of y equal to 0 satisfying these initial conditions. By the uniqueness theorem, we have pi equal to psi, or pi equal to C1 pi 1 plus C2 pi 2 plus etc. Cn into pi n. So the initial conditions for psi are equivalent to the following equations for C1, C2, C3, Cn. So this is a set of n linear equations for C1, C2, C3, Cn. The determinant of the coefficients is Orangton of x0, which is not 0 since pi 1, pi 2, pi n are linearly independent. They're linearly independent. Therefore, there is a unique solution C1, C2, C3, Cn of the equation. So this completes the proof. Next theorem. Let pi 1, pi 2, pi 3, pi n be n solutions of L of y equal to 0 on an interval I. And let x not be any point in the interval I. Then Orangton of x equal to e power minus interval x naught to x a1 of t into dt into Orangton of x naught. So now we prove this result for the simple case n equal to 2, and then we give a proof which is valid for general n. So now the proof for the case n equal to 2. So in this case, Orangton of pi 1, pi 2 equal to pi 1 into pi 2 dash minus pi 1 dash into pi 2, and therefore w dash of pi 1, pi 2 equal to pi 1 dash into pi 2 dash plus pi 1 into pi 2 double dash minus pi 1 double dash into pi 2 minus pi 1 dash into pi 2 dash. This can be simplified like this. That is pi 1 into pi 2 double dash minus pi 1 double dash into pi 2. Since pi 1, pi 2 satisfy this differential equation, then we obtain pi 1 double dash equal to minus a1 into pi 1 dash minus a2 into pi 1. Pi 2 double dash equal to minus a1 into pi 2 dash minus a2 into pi 2. Thus, this w dash of pi 1, pi 2 can be written as pi 1 of minus a1 into pi 2 dash minus a2 into pi 2 minus a1 into pi 1 dash minus a2 into pi 1 into pi 2. That is equal to minus a1 into pi 1 into pi 2 dash minus pi 1 dash into pi 2. This can be written as minus a1 into Orangton of pi 1, pi 2. So we see that the Orangton of pi 1, pi 2 satisfies the linear differential equation y dash plus a1 of x into y equal to 0, and hence the Orangton of pi 1, pi 2 of x equal to c into e power minus interval x naught to x a1 of t into dt, where c is a constant. By putting x equal to x naught, we obtain c equal to the Orangton of x naught. So thus proving this result for the case n equal to 2. Proof for a general case n, we let w equal to, that is Orangton of pi 1, pi 2, pi 3, pi n. So for brevity, from the definition of Orangton as a determinant, it follows that its derivative w dash is a sum of n determinants. It is w dash equal to v1 plus v2 plus v3 vn, where vk differs from w only in its kth row, and kth row of vk is obtained by differentiating the kth row of w. Thus we get this differentiation for the Orangton. That is w dash equal to the sum of n determinants in which all the determinant values are 0 except the last determinant, because all determinants are having identical rows except the last determinant. So w dash equal to only the last determinant. The first n-1 determinants v1, v2, v3, vn minus 1 are all 0, since they have two identical, each have two identical rows. Since pi 1, pi 2, pi n are solutions of L of y equal to 0, we have pi a power n equal to minus a1 into pi a power n minus 1, etc., minus an into pi I. Therefore, in this last row, that is pi I power n, pi 1 power n, pi 2 power n, pi 3 power n, pi n power n, all these values are replaced by using this equation. So in this determinant, all the first elements in the last row will be minus a1. So in every here we can take it out minus a1 as the common element from the last row. So w dash can be written as w dash equal to minus a1 into w. Then we get this differential equation, w dash plus a1 into w equal to 0. If you solve this differential equation, we get w of x equal to e power minus integral x naught to x a1 of t into dt into w of x naught. This completes the proof.